Hello, bachcho. Let's take a little trip to the late 1800s. Chemists were scratching their heads. Why did metal salts like cobalt chloride mixed with ammonia behave so weirdly? It was like the chemistry rules they knew were suddenly broken. Then came Alfred Werner, a Swiss chemist, the true Sherlock Holmes of coordination chemistry. In 1893, he boldly declared, metals don't just bond in one boring way, they have two bonding styles, primary valence and secondary valence. Boom! Mystery solved. Thanks to Werner, we could finally understand cobalt-amine complexes, and he even bagged a Nobel Prize. This was chemistry's version of switching from black and white TV to full color. Alright, let's decode these two valences. Primary valence is like your exam marks. They can change, they're out there for everyone to see, and in chemistry terms, they're ionizable bonds. They're usually satisfied by negative ions like chloride. Secondary valence, on the other hand, is like your close friendships, non-ionizable, unshakable, and they define your coordination number. Take cobalt hexamin chloride, written as open square bracket CONH3 6 close square bracket Cl3. Here cobalt has a primary valence of +3, shown by the 3 chloride ions outside the bracket. Its secondary valence is 6, shown by the 6 ammonia molecules inside. When you dissolve this in water, the chloride ions wander off like students after school, but the ammonia ligands stick around like best friends. See the difference? Primary is loose, secondary is loyal. So what exactly is a coordination entity? Imagine a cricket team. The central metal is the captain, the ligands are the players on the field, and together they form the coordination sphere, which is always written inside square brackets. Outside the bracket, you've got counterions, like the substitute players or the fans cheering from the stands. For example, in open square bracket CONH33Cl3 close square bracket, cobalt is the captain, 3 ammonia molecules and 3 chlorides are the players, and any extra chloride ions outside act like spectators. The strength and number of these metal-ligand friendships decide how strong and stable the whole team, the coordination entity, really is. Now let's talk about fashion, chemical fashion. Ligands don't just crowd around randomly, they arrange themselves in neat geometrical shapes called coordination polyhedra. If the coordination number is 6, they dress up in an octahedral geometry, like cobalt hexamin, written as open square bracket CONH3 6 close square bracket 3+. If the number is 4, they can either go tetrahedral, like nickel tetracarbonyl, open square bracket NiCO4 close square bracket, or square planar, like platinum tetrachloride to minus, open square bracket PtCl4 close square bracket to minus. And trust me, these shapes aren't just for style points, they change real properties like color, magnetism, and reactivity. Basically, the geometry is the haircut of a coordination compound. Change it, and the personality changes too. Now comes the really juicy part, isomerism. It's like having two students with the same name but totally different personalities. Coordination compounds with the same formula can look and behave completely differently. First, stereoisomerism, geometrical isomers like CIS and trans, or optical isomers that are mirror images. For example, cobalt with 2 chlorides and 4 ammonias, written as open square bracket CoCl2 and H34 close square bracket plus, has a CIS form where the 2 chlorides are sitting together, and the trans form where they sit apart like sworn enemies. Then we have structural isomerism, linkage, coordination, and ionization isomers. Take cobalt pentamine chloride sulfate, written as open square bracket CONH35Cl close square bracket SO4 versus cobalt pentamine sulfate chloride, written as open square bracket Co NH35SO4 close square bracket Cl, same formula, different structures, different behavior. And here's the kicker, in real life, this matters a lot. One isomer of platinum saves lives as a cancer drug, cisplatin, while the other isomer, transplatin, is basically useless. So kids, never underestimate the power of small structural changes. Alright, time to wrap this up before the bell rings. Werner taught us that metals show two valences, primary, the ionizable kind, and secondary, the non-ionizable kind. Together, the central metal and its ligands form a coordination sphere, and the way ligands arrange themselves gives rise to geometries like octahedral, tetrahedral, or square planar. These shapes then lead to isomerism, both stereoisomers and structural isomers, which can totally change the compound's properties. Werner's theory solved the chemistry puzzles of his time and gave us the foundation of modern coordination chemistry, which now shows up in metallurgy, biology, and medicine. So the next time you see hemoglobin carrying oxygen in your blood or hear about a platinum drug treating cancer, tip your hat to Alfred Werner. He turned confusion into clarity and in the process made coordination chemistry one of the coolest parts of our subject.